Hello guys, welcome back to this channel. This is second lecture on subgrade soils. So another important test to determine the characteristics of subgrade soils is Atterberg limit. So this Atterberg limit is important concept in fine-grained soils, since fine-grained soils have different status when in the presence of moisture content. Their engineering properties is significantly affected by water content and mineralogy. What's meant by that is, suppose you have a soil sample mixed with excess amount of water. So this mixture will act as a viscous liquid, a viscous fluid or a viscous liquid. If you intentionally reduce the water content by exposing it to the atmosphere, or reducing the water content using an oven, uh, it will reach a point in which the soil stops behaving as a liquid and starts behaving as a plastic. This limit is known as liquid limit. Further reduction in water content will ensure the soil to behave as a plastic material. You can mold it with your hand. It shows deformation. But further reduction in water content will reach to a point in which the soil will show a visible deformation cracks. This limit is known as plastic limit. And further reduction in water content will lead to a point or a limit in which the soil will no longer shows a volume change. This limit is known as shrinkage limit. So to summarize, the liquid limit is the limit in which the soil stops behaving as a liquid and starts behaving as a plastic. The plastic limit is the limit in which the soil stops behaving as a plastic and starts behaving as a semi-solid. And the shrinkage limit is a limit in which the soil stops behaving as semi-solid and starts behaving as a solid. As you can see, there is a volume change between liquid limit and shrinkage limit, but after shrinkage limit there is no volume change, since there is no presence of sufficient water. So what this tells us is fine-grained soils can occur in different status when they are exposed to different moisture contents. And with an increase in water content, the soil will have lower shear strength and hence will have higher settlement, since settlement is related to consolidation and consolidation is related to volume change of a soil. So this liquid limit, plastic limit and shrinkage limit are collectively known as Atterberg limit, and from these three limits, liquid limit and plastic limits are important and are used in many engineering estimation or calculation. So the liquid limit is usually determined using Casagrande apparatus. You can see this apparatus on the left side of the slide. So using this Casagrande apparatus, you can determine the liquid limit, and manually you can determine the plastic limit. We'll see this in the next few minutes. So another important concept is liquid index, or is a measure of the soil shear strength. For fine-grained soils, you can measure their strength using liquidity index. If liquidity index is less than 0, then the soil will have higher strength and it will almost be in semi-solid state. And if you have a liquidity index greater than 0, which means greater than 1, then the soil have low strength and its characteristics as is like a viscous fluid. So how can we determine Atterberg limits? Atterberg limits are determined using Ashto's manual. So there are a series of procedures. The important procedures are laid down below. First, you need important tools such as Casagrande's apparatus, soil mixing pan, moisture cans for determining water content, spatula for mixing the soil sample, grooving tool for making a groove. So the first step is to prepare a soil mix sample having almost 150 grams of soil passing number 46, that is 0.425, less than 0.425. You mix that soil with distilled water, and you place the place the prepared material in a storage dish and cover it with a towel in order to prevent evaporation. You let that sample settle down for about 16 hours so that there is a proper so that the soil is properly mixed with water. Transfer the soil into the brass cup using spatula, and when you transfer that, you have to be important not to create water bubbles. So in order to not to create air bubbles, you have to form a smooth fewer strokes. You have to use smooth fewer strokes. Then you have to form a groove from the highest point to the lowest point on the brass cap, and you let the rotation of the brass cap be commenced. So the number of rotations or number of blows required to close the groove at about 10 to 30 millimeter. And when the two grooves comes in contact, you record the number of blows, and you take the representative soil mass for further moisture content determination. You repeat the trial for about 3 times by increasing the water content. So how to determine plastic limit? In order to determine plastic limit, you have to take 20 grams of soil from previously prepared material for liquid limit test. You reduce the water content by either drying it on a glass plate or molding it using bare hands. Then you apply a pressure using your palm finger on a glass plate. You roll it on the glass plate with sufficient pressure until it reaches a diameter of 3.2 millimeters. The concept behind this is when the soil sample reaches about 3 millimeter or 3.2 millimeter, it starts to crumble and shows visible cracks. So this point is known as the plastic limit. Mind you, you do not have to exert additional pressure so as to you intentionally reach the soil sample up to that point. So you have to be gentle and apply a moderate pressure. Finally, you have to break the rolled specimen and put it in moisture cans and determine water content. Precision of the results. So these Atterberg limits are usually values show deviation between different operators. So this table shows a deviation, the acceptable deviation between different operators in a single lab and with multiple laboratory. So you have different types of soil such as highly plastic clay or lime clay, or you have silt, plastic silt. So the standard deviation values and the acceptable range between different liquid limit, plastic limit and plastic index values are shown. So even if this must be so these are the acceptable ranges. Let's see Atterberg limit using practical example. The following results were obtained from liquid limit test on a clay soils using Casagrande's apparatus. So we are given with the number of blows and water content corresponding to each number of blows, and we are required to determine the liquid limit of the clay sample, and we are also required to calculate the liquid index and plastic index. So you know that the liquid limit is the water content corresponding to 25 number of blows. So since we are given with the number of blows and water content using semi-log scale on x-axis, logarithmic scale we plot the number of blows on y-axis using ordinate scale. We plot the water content, and the pointers usually do not lie on a straight line, so we have to make a trend line, linear trend line. And using linear interpolation for 25 number of blows, we can determine the liquid limit. So the liquid limit is about 40, and this curve is known as flow curve. This curve is known as flow curve. So once we determine the liquid limit, we can determine the liquidity index and plastic index. So the plastic index is the water content in which the soil behaves as a plastic material, so it gives us the water content. So the liquid limit minus plastic limit will be the values of plastic index. Plastic index will be 40 minus 23, and it will be 17. So this value 17 represents the soil is moderately plastic. It's not highly plastic, it's moderately plastic soil. The liquid index is the natural water content minus plastic limit divided by plasticity index. So the liquid index is about 0.88. Mind you, the liquid index is a representation of the shear strength of fine grained soil. So if the liquid index is between 0 and 1, then the soil is in a plastic state and have intermediate strengths. So this is all about Atterberg limits. Next video we'll see about soil compaction. Thanks guys.